Last month we did a session about cryptography. This time we're going way down memory lane and looking at Voron. Now, Voron is the baseline of everything that we do. It was started, the project, something around 2012. So just to give you some context about how it works. Voron is the storage engine. This is how we write bytes to disk. The first storage engine that we use was something called ESENT, which is an embedded storage engine that comes with Windows. This is now open source if someone wants to read out of C++. We really wanted to have a managed project. So we wrote something called munin, which is based around concept of LSN, log structure merge things. There is the database internal book upstairs. I think that last I saw it, it was with the FATS, and it gives a really good coverage of the topic. Eventually, we started writing Voron, and a lot of the things that we wrote in 2013, up to 2015, 16 are still there today, unchanged. We were recently looking with Federico over how we can improve performance. It turns out that code that we wrote in 2014, when opening a transaction, caused us to do a lot of locations. Now, a lot of location is in our terminology. Allocating an object is way too much. So there is now work on reshaping how we are currently going about building Voron, going back all the way to the original code. And literally, you go to the code base, you run blame, it's 10-year plus code base, which is really encouraging, because that means that it's very stable. It's really fighting, because if we have to touch it, that means that we have to touch really core pieces. And more interesting, it means that no one really understands what's going on. And I'm speaking here as the person who wrote a significant portion of this code base. 10 years ago, no kids, more hair, no idea what's going on. Okay, so Voron is actually composed of multiple layers. There is the bottommost, we write to the disk. On top of that, we have transaction, journaling, data structures, memory management, a whole bunch of stuff. I cannot cover everything in a single session, so I'm going to cover the bottom parts first, and then we'll cover other things as we go. So this is what we're going to be talking about. We're going to talk about from the bottom up, how do we build transactions, and how Voron manages files, what is his data model, and most interesting, what happens when things fail. Typically, we tell results. Okay, so here's the problem. These are nasty. Nasty in the same way that you go in the sink and nothing has been washed in 3 weeks and you have maggots, kind of nasty. Why do I have this imagery in my head? Because everything that you know about writing to the disk is a lie. Let's say that we have Igor. Igor has 4 items he can keep in his head. Okay? And that is memory. And now he wants to do something with that. He wants to do something that needs more space. So he has to take that bit of memory and write it to the disk. Where is the disk? If we're talking about Igor is here and I can ask him a question, Igor, remember that x equals 3? Okay. What is x? Sorry. Okay. As I said, these are unreliable. But if I ask you, if I tell you to remember that x is 3, and now ask you what is x? 3. Okay, great. Now remember, you only get to remember 4 things. When I tell you the 5th thing, you have to write it to disk. Now, here is where it gets interesting. Why? Where is the disk? In the parking lot. No elevator. He has to go down 7 floors, then go back 7 floors. Okay? So remember 3, 2, 1, 0. Now remember 6. In order to remember 6, he has to spill something to disk. Okay, now you can see going up and down. And this is a huge problem because Igor doesn't like going on the stairs 6 times a minute. What do? He's cheating. I told him, write to the disk x equal 3. He's going to put it in a box, things to take to the parking lot, and keep it in the box. From my perspective, I told him to do that. It was done. I move on. And then at some later point in time, he says, oh, I have enough items in the box, or it will be enough time, and I'm going to take all of those items to the parking lot for storage. Great. Along the way, I fall down and trip the stairs and lose everything. What's the problem? Think about the sequence of events. I made a write. Please be safe. Tell me, okay, I'm done. Is it safe? No, it's not safe. Now, here is a really creepy part. He can remember 4 things, but he needs to use some of that memory to remember the things he needs to write to the disk. Okay? So this line, when you call write, they don't do what they say they do. Even worse than that, every single piece on the storage hierarchy would lie to you. What do you mean by that? Igor isn't actually going all the way down to the basement. He's going to meet that guy in the elevator, and that guy is going to take it downstairs. And that guy also is going to have a box of items, blah, 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 blah. It buffers all the way down. Buffering memory means that it's not there. It gets more interesting because there is zero guarantee about ordering. So you go to throw everything into a box. Eventually it will get down. It is entirely possible that things that are wrote later will be written and things that are wrote before will not be written. So that makes writing to the disk a horrendously complicated task. Why does it have to be this way? Because disks are slow, ridiculously slow. So we want to pretend that they are fast. So that's the number one issue. So whenever we have to write a disk, we have to jump through a lot of hoops. And we have to understand that we have to also take into account that this is slow, and I cannot afford writing to this all the time, and I cannot afford not being transaction. So let's see how we do that. Meet Voron, and what's the idea now? I went kind of crazy with the Jenny. Huh? Yeah. Notice how this is ruling all of the hard disks in the world, pretty much. So the first thing that we have to understand, we are not typically reading or writing directly from our files, which is really weird. We have files. We're not reading or writing from them. What's going on? We're using memory map. What is memory map? Sorry?
File of the memory.
We are telling the OS, here is this file. It's this big. I want you to pretend whenever I reach this piece of memory, it should reflect what is in the file. Now, this has a huge impact on us. Why? It means that we don't need to manage the buffer. As a trivial example, I need to go to this location. So I would go to this location by just pointing the memory, just reading or writing to the pointer. It's the responsibility of the operating system to do things like, oh, it's not there in memory. I don't have it in memory. I have to go and fetch it from the disk and do everything around that. Not having to manage buffers means that we are relying on someone else to do that. Who is that someone else? The operating system. This is beneficial for us because we benefit from IO coalescing, which is multiple requests being merged, read ahead, read behind, those are things where we have good strategies built into the operating system already to manage that. It also means that the operating system is responsible for evicting our memory. If I'm asking Igor now, remember X is 3, and then I'm not touching X for a while, the operating system will write it to the disk and remove it from memory. So this is awesome. It also means that we have a really good story around how do we manage running as part of a more complicated environment. It's not just RavenDB on the machine. You have RavenDB and Node.js and Nginx all running together. How do we make sure that we're not stomping over each other? By utilizing the memory map, we're telling the operating system, I want you to manage that. So I'm being a friendly neighbor to all of my other processes. It does have a huge impact on the code. Why is that? Because it means that I have a page fault to deal with. I'm accessing a pointer, and it's possible that this would trigger page fault. Page fault is synchronous operation. This means that under load, we might store a lot of threads. The benefit of that is that the programming model is a lot simpler and cheaper to work with. But this is an issue that we have to think about. Okay, so let's talk about paging. What are pages? In order to understand that, I'm afraid that I have to go all the way back to the 8086 CPU. 8086 CPU was using something called real mode. You told the CPU, I want to read address X. It went and read the physical address X. Okay, that's great. It's very simple, but it lacks any sort of protection. Modern CPU, by modern I mean everything from the 286, roughly 1985, have something called virtual memory. What is virtual memory? It basically goes like this. Inside the CPU, there is a register. The register contains the mapping. So you access a piece of memory, and this is a virtual address. The CPU consults the table, says, oh, you access pointer at X. This actually translates to Y in the physical memory. This is how operating systems are able to maintain isolation between processes, among many other things. It also means that this is how the operating system implements memory map files. How? It maps the range of memory, but says, I have nothing here. When the CPU tries to access a piece of memory that is mapped, but doesn't have actual data, it calls to the operating system using a page fault. And then the operating system handled that by reading from the disk, putting the data into memory, and then moving on. Now, the unit in which we are working on is called the page. In x86, it's always 4 kilobytes. In ARM, in Macintosh, for example, it's typically 8 kilobytes. Voron works in pretty much the same way, but it uses 8 kilobyte pages. Now, we have to understand this is super important. Everything is a page. Now you can see this cutie here, and they hold a page with data. And everything has to fit into one page. So everything is structured up. If I have a value that is bigger than one page, I allocate multiple pages in a consecutive order and use those. And that's it. Now, why does it matter? Because it means that I only need to refer to a particular page, and then I have some internal structure inside that page to do something with it. Okay, So you can see below, this is how I read on the disk. This is the code. So you get me a page, and the page gives me a pointer. Then I can cast the pointer and do something with the page header. The moment that I actually try to read or write the data, this is when I'm actually reaching into memory, maybe doing a page fault or something, but that's about it. Conceptually speaking, we have a buffer in memory that reflects the data on the disk. That's about it. This is not actually true for three reasons. One of them, if we have encryption, then the data is encrypted, so we cannot just give you a pointer. We have to first get the encrypted data, decrypt it into local buffer, and then give you the decrypted buffer. If you're running on 32 bits, it's also more interesting because I may have, right now I'm using a 5 gigabyte database on a 32-bit OS. I cannot actually access 5 GB, I cannot map 5 gigabyte. So I have to map a section of that each and every time. But conceptually, this behaves very much like this is in memory. There is one problem, even if I'm running without encryption and without 32 bits. And that happens, what happens when the file grows? So think about it like this. I have a file, it's this big. I map it into memory. Now I need to increase the size. What do you do now? What about this piece? Now, it turns out that there is a hidden assumption inside of Voron that in order to do things properly, I must be able to map the entire range in a consecutive manner. How do I deal with that? Remember, right now, Shiran is a transaction. She's now looking at page number 300. Igor is another transaction that just needed additional disk space to increase the disk space. But we have a concurrency issue because I cannot increase the size of the mapping. Why not? Because eventually, memory fragment, I have some memory here that already used for something else. But the opposite is by something, so I cannot just extend the memory. I have to find another solution for that. I can also not just unmap this memory and create a new one. Why is that? We have Shiran currently looking at the old memory. So we use a very simple trick. We map it again. So we have this memory, and we have this memory in different locations, and this part are basically alias to the same values. So those are two virtual memories that point to the same physical memory. With me so far? Yes. So we have two memory mapping, one used by Shiran, one used by Igor at the same time. Okay, so now, what does this give us? It gives us a major reduction in complexity. It does mean that we have to deal a lot with minutiae of memory management, and it's something that we have to deal with quite a lot. Now, as I mentioned, I cannot just write. Why cannot just write to the disk? Because the disk is horrible. But even assume that they have the best disk, I still have another problem. I have Shiran currently reading from the database. I have Igor currently modifying the database. What happens if they're trying to look the same thing? Shiran is currently looking at recent order. Igor is trying to update that. What do we have to do? How do we manage that? I can try using logs and all sorts of other nastiness like that, and also note things that I want to do. There is a really good paper called OLTP through the looking glass, who analyzed the performance of database engines. Many relational databases are spending over 30 to 40% of their time just managing logs. So with Voron, we decided to go another way, and there are no logs in Voron. There is a single write transaction, but concurrently, we may also have many read transactions. So we have to solve this problem. So here is a very simple solution for that. Igor can never modify something that Shiran is seeing. But I don't know what Shiran is looking at. So basically, Igor cannot modify anything on the file. So when we need to modify something, we use a process called copy and write. We take the page and we copy it to the side. And now I have my own copy that I can mutate in peace. If Igor decides that he wants to roll back the transaction, what happens? Oh, that's not something. We just discard all of these allocations and we're done. Nothing happened. What happens if you want to commit this transaction? Then we need to publish those changes. Remember, we still have Shiran reading the code, reading the old version. So this is the process that happens. Okay. You can see that this is Igor. He is putting probably contact license, color contact license. Okay, and when he wants to modify something, the board is the actual data file, and he's copying stuff down and modifying them. At the end of the day, what do? We need to commit. So we take all of the local modified pages. This represents the change set of this transaction. Now, this is really important because it does not represent operations. It represents the physical changes made on the memory. Why does it matter? Right now, Igor wants to make a modification. He does that. And we record the result of this modification. It means that if I want to add a new operation, for example, compact trees for Corax, SIMT or any of those things, I don't need to worry about the storage layer. The storage layer is just giving me buffers and managing that. On commit, I take all of those modified pages, and then I do something really interesting. I dip them with the previous version. Remember, the first thing that I did is I cloned them from the original copy. So then I just do a binary diff between them and write just the modified bits. Why is that? Because Igor changed the status of an order from ready to shipped. We modify a whole page, a kilobyte page, but practically we only modified 8 bytes. So this gives me a really good way of just discarding everything that is already in the same, did not change. Then I take all of those diffs across all of the pages that are modified, and I'm compressing them. This is because these are slow. Right now, we're using LZ4 algorithm to do that. We're thinking about switching to ZSTD because it's actually faster and cheaper to do that. And we end up with a compressed buffer that holds the diffs of all of the modified pages in the transaction. Follow so far? I intentionally am not showing code. I want to give you the concept, not here's how it works. But now we have a problem. What do we do with that? Those are all of the modification in that transaction. And now we need to write it to the disk, right? Because now we commit the transaction. Except that this would be unacceptably high cost. Why is that? Here is my transaction. It modified 5 pages, somewhere in the file. What happens if I want to write them? I have to wait until it actually physically hits the disk. So that means that I have to make many different I/O operations, each of them is incredibly expensive, probably in a random manner. So right here, right here, right here, right here. Think about it in the same manner that you have a physical notebook. Give me the So here is the physical notebook. And now write on page 6, write on page 430, write on page 600, etc. This is super expensive. Just switch it to the right page. And remember, we're working in mmap files. The unit of change that we have here is the page. So every time that we write to the file, I change 8 bytes. I need to write 4 kilobytes at minimum. That's really, really expensive. I cannot afford doing that. Beyond that, I have another problem. Shiran is looking at those files. So Shiran is called to looking at this page. What does it mean? I cannot change that, but I need to commit a transaction. So what's going on? I have, in addition to this data file, I have another file called the journal. Okay, and the journal is really cute. We open that using these flags, and the most important here is the ODSync and ODirect. What does it mean? Those two flags tell the operating system, I'm going to make direct IO calls to this file, bypass all of the caches. It requires that all writes would be page aligned, both in memory and how we write to the disk. It bypasses all of the buffers, and when you write to the actual disk, it writes with a flag that is called FUA, Force Unit Access. Basically, instead of having buffer, it says, go all the way down, tell me when you finish writing. As you can see, this can be expensive. Okay? So we cannot make that, we're trying to make it as efficient as possible. So one of the things that we're doing, we are writing to the journal always in a sequential manner. So think about physically how it works. I'm writing. Now switching to the next page is super easy. Jumping to this page is much more expensive. I like having props. And it's funny because if I have this prop, it makes it so much easier to actually explain what's going on. A page is literally a page. So going to this is expensive. That's why at a higher level than Voron, we have the transaction merger, which allows me to take multiple independent transactions and merge them into a single write to the disk. It also has an interesting observation. Let's assume that Shiran, Stav, and Shahar are currently writing to me. I accept all 3 of them and all 3 operations. Do this operation, and then I created a storage transaction that is composed of all 3 of them. And then now writing that to the disk. This is slow. While I'm writing that to the disk, I already done all of the in-memory work of building the transaction, of prevent the transaction. Now I have a transaction coming from Omer. And now remember, I'm currently writing to the journal, and I already start processing the next transaction built on top of speculative transaction state because I haven't actually finished committing that to the disk. This is called the async commit process. And if this fails, if this write to the disk fails, this is a catastrophic error. Basically, it means that something is so broken I cannot write to the journal. We're basically at that point saying, I'm done. I'm aborting all the transactions. I have to shut down the Voron instance and recover. We'll talk about this in a bit. Why is that? Because now I have an error writing to the disk. There is a disconnect between my in-memory state and what is written here. And I need to be a transactional database, which means that there must be a sync between them. Okay? Why does it matter? Why does it matter that I have to start over? The write failed. Why can't I just, okay, I can roll back the transaction and try again with a new one. The issue here is that failure doesn't mean what it says it does. For example, if I tell Igor, give me $1 billion, he's going to tell me insufficient funds probably. Okay. Now, if I'm going to tell now, it works. Okay. And at the end of the transaction, at the end of the operation, no change has changed. No state has changed. Now, if I go and tell him, give me a fork, bring the fork in front of you, give me a fork. Please. Yes, please. Again, I do forks. Okay, another fork. Okay. And give me another fork. No, I don't want to talk to you now. What is the current state on the disk? The fact that I had a failure doesn't mean that the state on the disk actually failed. It is possible that I actually have all three of those, but when I'm trying to tell him, yeah, I wrote it, and it says, this is written, it's there. So on the disk, I have committed the transaction. As far as Igor is concerned, the transaction never happened. So we have to start from scratch. We have to verify what is actually on disk. Question so far on the journal.
No.
During normal operations, we only write to the journal. This is one of the most expensive things that we can do. This is the source of latencies to I/O, those things. Let's see that. Okay. Igor finished the transaction. What happens now? Now Perman wants to run a transaction. Firan is still currently reading this page. This is the page that says, how long do we have till this lecture ends? And Igor updated it, and now Perman wants to read it. What's the problem? Firan is reading this page. I cannot modify this page. He wants to read the updated values. In order to do that, we have something called a page translation table. So one of the things that Igor does when he commits a transaction is publish his page translation table. This is basically a dictionary of a page number to a pointer. It's a little bit more complex than that, but that's the concept. And when he commits a transaction, he publishes, here is the new page translation table. Now Perman is saying, hey, I want page 4. And he gets pointed to this page 4, which is the temporary scratch copy that Igor did. What happens if now Perman wants to modify this page?
Modify the updated data.
Sorry?
Modify the updated page.
Okay, but now I have a problem because Tav is also reading the updated page.
Write a new scratch file.
So I have to copy the file, the page again. At which point I have, you know what? Let's do it physically. This is the original page. No, I want a pen, right? Okay. No, not this one. Okay. Here is page number 4. This is on the physical list. Okay? Now, I need to modify it. So I took a new page. This is Igor. And now hold it so people will see. Okay? Yay! Okay. So, and now this is the page. Now we have 2 versions of this page. This one and this one.
This memory?
Sorry?
This one on memory.
This one is on memory and currently drawn that. He's currently writing on the page. Okay. Now we want to publish that. And in order to publish that, we do something like this. Okay, here is page number 4 that is published. At this point, we have 2 copies. Shiran knows that when she wants to talk to read page 4, she goes here. Carmelo, when he wants to go to page 4, he goes here. Why? Because of the page translation table. Now, when we have Carmel wanting to make a modification, well, he does this. Okay.
Why should the other be what the gold is?
Yes. Okay. So right now, here's the situation. Stab is reading what? No,
No,
this is Carmel.
No, this one. I think.
Stab is reading this one. Shiran is reading this one. Carmel is reading and writing to this one. No, that's that. Okay. And at the end of the day, we're going to make it really confusing to the people. No, this is actually page 4. Please notice that. And so now we have 3 different copies of this page. By the way, doing that with physical stuff versus trying to draw on or diagram on PowerPoint, so much easier. You understand how it works with regards to multiple copies, and the only thing that we need to do in order to ensure that it worked through the page translation table. That's perfect. And this thingy is called MVCC, Multi-Version Concurrency Control. It's a very fancy name to bunch of pages on the board.
Why you don't want to hold the read transaction too long?
Yeah. Okay. So here's the problem. Avivna wants to write something. What does he do?
If you wait for the people to finish,
No, he does not wait.
go to the table and take the last.
He takes the red one. Okay, and does the same thing, probably in green, whatever, because that's the color that they have available.
What happens if Shiran wants to write?
She cannot. She's a read transaction.
Okay.
This is actually a really important concept. Voron has single writer thread. It's actually single writer. Practically speaking, we have a dedicated thread, both for cluster operations and for the database that does the writing.
Yes, a lock. Right?
Yeah, but that lock is usually not engaged because only one thread is doing the locking.
Okay.
So in this case, and again, using physical example, a writer is Shiran. She physically has a pen and paper. If you want something to be written, you have to go to her to write. Now, we could try to do some negotiation. Can I have the pen and paper? I would write it. But it tends to be much cheaper, easier to have her write it because she can aggregate multiple transactions in the same sense. Okay, so far?
Yeah.
Okay. Now, Shiran is back being a read transaction. Aviv is now a write transaction. He wants to modify this page. What does he have to do? He goes to the read one, the last one that was modified, and copy it again. And now Shachar wants to do that. And now, what's the situation? We end up consuming all memory in the system with copies of the same page. Why is that?
I have a question about the old.
Sorry? Yeah.
When you go and the write on the black version, it's free that the page of memory. It's free the memory.
When you go did what?
He ends the writing. He commits
the data. He writes the data to the journal. He cannot read his memory. Why? Because we have Carmel who now wants to read Igor's modifications. He has to read it from somewhere. So now we have Shiran, who is currently reading a backup, is currently reading the database, and a lot of modification on that. This creates a lot of copies of the data that are maintained in memory until Shiran closes the right transaction, the read transaction. What happens then? Why do we have to wait till Shiran closes the transaction? Because until we finish waiting, this cannot change because Shiran read it once, and for consistency, she has to always read the same thing. This is how we implement snapshot isolation. So a single transaction has a snapshot view of the entire database. Right now, it also means that we have to keep track of all of those values. Conceptually speaking, and something that we are looking into trying to implement, we can only keep the version that has associated transactions with them. Why does it actually matter? The most complicated scenario is backups. Try to imagine to have a backup of a terabyte database that has a lot of writes. How does it express itself? I have a long-running read transaction and a whole bunch of modification that I have to deal with. That kind of sucks. Okay?
I have a question. So those are the scratch files?
Those are the scratch files. No.
But you didn't mention how you told us that this is in memory.
This is in
How
memory.
do you write it to the disk?
I do not have it.
But there is...
One second, give me a second.
Right. This Shiran and
Okay, next page. Okay, Shiran completed her transaction. What happens? That means that no one, all of the transactions right now, almost started new transaction. What page is he reading? This one.
The red one.
yeah, so that
What does it mean? There are no observers for this one. Copy this. Remember, copy, because we have someone looking at this. And write it into here. So pretend that I'm not copying this. I'm writing it into here. And now I have to update the page translation table for the next transaction. So now, starting opening the transaction, both of them are in
How
transaction.
does it happen on the right log?
No, there is, okay, this is super complicated part of the code that we really like to change. There is a right look and a flat look. And the actual issue that we have is that after I update this, I need to update the page translation table. I need to do that under the right look. The problem here is that I don't want, so every now and then I have a flashing text, all of those pages I'm writing to here. That's great. What's my problem? It happened in a background process. Let's assume that I'm writing, eventually need to make this sort of update. I have to do it under the right look. But then, I'm writing. Try writing, please. Very first right, okay. Okay, good. Try to imagine what it does to your latency. So here is what we do.
Why not put that under the transaction manager?
Yeah, because the flashing operation is not done by, it's done in a separate thread from the transaction manager. This leads to a lot of issues about priorities. I will talk about after I finish this, but let's talk about how Shiran is. Please write. Okay, and I'm doing something like this. I cannot take the pen, I'm giving it to her. And I make you notice, when you have time, please also write those things for me and let me know. So we're basically giving her a task to do. All of which, by the way, this is what I'm talking about when I'm talking about 10 years old code and the complexity associated with it. So now, we need to flash from all of those scratch pages into the disk. We are doing that by finding all of the modified pages that no one is looking at. That there is all of the transaction have done beyond that stage, then we can do that. Once we've written the data on the scratch files, on the scratch pages, we can reuse that memory, we can free it, etc. Remember that at that point, I also want to delete the data from the journal because I've already written that to the disk, except that I cannot do that. Why is that? Because the disk will lie. I just wrote all of those pages to the disk and I'm happy. Then, you know what happens? The system crashes and it goes like, I don't care about this. Or even worse, it's somewhere around here. Some part of it is the old version, some of it is the new version, and you end up with what is basically crap. Let's go back here and I will show you physically what this crap looks like. Can I have the pen? So you get something like this. This makes me very sad. Okay? So we have a commit process. We have a flashing process to take all of the modified pages from the temporary storage and write them to the disk, which is still not sufficient because now we also have a sync process. What is this sync process? This is the process where saying, okay, I finished writing a whole bunch of stuff to you. Now I'm going to issue a command called fsync. Actually, fdatasync is what we want to use, but we're using a system called msync because we're working on memory map data, details that you don't care about. We're issuing a sync command, and that tells the operating system, I want you to write all of the data to the disk, and only come back to me when you're safe and sound, and this is actually on persistent media. As you can imagine, this is horrendously expensive. So we're trying to do that on an infrequent basis, especially if you have lots of very large databases. After we got a successful result from msync, only then we can consider the journal is okay and we can remove it. Okay, sorry?
Recycle.
Sorry?
Recycle it.
Recycle it, yes. I will touch on that in a bit. And remember, throughout all of this process, at any given point in time, I must be able to recover from a failure, including nasty failures like this thing, where I have effectively data corruption. Okay, let's talk about prioritization. One of the things that we have to deal with is what happens if I have more than a single Voron instance in my system. For example, I may have a Voron database and 3 indexes. How many Voron instances do I have? I have 4. Actually 6, but we don't touch on that. Okay, there's some other things that we're using for configuration and cluster and a bunch. So what's the issue? The issue is that now we have competition because, yeah, we're using different files, all of which are sitting on the same physical location. So now both me and Igor are trying to write at the same time. Now we write to different pages, but I can sort of, please write like this. It's not really useful. So the flashing operation is done in a background thread that is global to all of the Voron instances in the process. And the reason we do that is so we can limit the amount of concurrency that we use to avoid doing that. Now, here is another important aspect. How does flashing work? This is some memory values. This is some items in memory. Here is a memory map page. Here's memory map file. How do we flash the actual data? Use memcopy. So this is intended to be memory-to-memory operation. flashing, even for very large amount of data, is expected to be very fast. When wouldn't be very fast? When it triggers page faults. So if we see flashing that takes a lot of time, that's a good indication that there is a problem with I/O memory and those sort of things. After the flash is completed, then we can issue the sync command. And again, this is throttle to avoid hammering this too much, blah, 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 blah. Questions so far? Okay. Yeah.
What about this file, this scratch page?
The scratch file, the scratch pages, yes. What about them?
We are sending it to
No.
this.
No, we're not sending them.
Only the-
When we flash, we copy the last version.
Only the last one.
Yes, because I don't need to copy Igor changes. I already have command changes, we overwrote it. Okay. Really important to remember what you see here, this is the full page. The journal, we wrote the diffs, but the scratches holds the whole page. Okay. Questions so far?
I think I have a question.
Yeah.
From the client point of view, when is the transaction considered committed? When it is written to the journal, or when it comes back from the F-sync?
When it's written to the journal and the journal said, I successfully complete this part.
So when it comes back from the flushing, from the F-sync?
No.
No. Let me, oh. So here's the deal. We started with writing a transaction to the journal. Igor is committed a transaction, he wrote something, and now he gave it to the journal. It's in the process of being committed. While it's been in the process of being committed in a synchronous fashion, he's already started processing Omer's transaction. We did not acknowledge the transaction completion to the client yet. When would we acknowledge that? When the journal file would say, I successfully complete this write. Make sense?
Complete as in writing
I
persistent.
finished writing that, yes. So to give the context, try to imagine there are two people here. You have here Igor, who is doing the business logic of deciding what should be changed in the pages. You have me, who is writing those changes to the file. So right now, Igor is done with his changes, and he says, here are the changes that I want you to record. I'm going to start doing that. While I'm doing that, he's now processing Omer's transaction, which built on top of the previous not yet fully committed transactions. Once I'm done writing the transaction details that he gave me, I'm going to tell him, okay, you can move on. That's the point when he's going to actually notify you that your changes has been committed.
Okay.
Okay. Now, let's talk about recovery. When we write to the journal, we write using OD-sync and ODirect. It means write directly to the physical medium. We do that to avoid buffering and having to make separate system calls that would do the work. So far, so good. It has limits. I can only operate on 4K boundaries and on 4K sizes. So when I need to write a buffer, I need to write something to the journal. I create the in-memory buffer for that and align that on 4 kilobytes. So far, so good, very easy, very simple. When I read, the first thing that I read from the journal is the transaction. This is a 64 bytes value, I think, or 128 bytes value, something like that, that says what data do I have in the transaction? How many pages? What are the page numbers? What is the transaction checksum? Because I do not trust the disk. So the first thing that I do is I start reading from the beginning of the file, and I verify that this is a valid transaction. Awesome, that's great. Now, I validate the transaction by reading the transaction data, computing my own checksum, and checking if this is okay based on what we have on the transaction header. Only at that point is this considered to be committed. Now, it is possible that I have a transaction header that says, oh, I written 10 pages and the file ends after 4 pages. Invalid. It's possible that the checksum that I have in the transaction and the checksum that I have in the committed is also invalid. Doesn't matter, it's invalid. There is a lot of work around managing that. It's even more interesting when you realize that if I have an invalid transaction, I don't stop the recovery process. I keep on reading to the end of the file. Why is that? I need to go out from this transaction is corrupted. I assume this is so I don't know if this is an uncommitted transaction or partially committed transaction or an actual file corruption, because here I have a valid transaction, but I don't have enough state to move to that. Other things that we have to take care of is it is actually possible to find a valid transaction in the file that is an old one. What do I mean by an old one? Instead of deleting and creating files all the time, which create a lot of work to the file system, we reuse the files. So we have journal number 2, we written a whole bunch of data to that, and now we want to update that. What we do is we write garbage to the first item in the file, and then we start writing actual transactions. So it is possible that you wrote a transaction, and immediately following that, there is a valid transaction that is old. So we look at the transaction ID as well to verify this is the case. On recovery, we read the transaction, verify it, and then we unpack it. We decompress the data, and then we apply the diff, because remember, what we actually write into disk on the journal is the diff. And we have to apply those diffs across all operations. So each transaction, I make a diff, and I apply the diff, etc. Why do I have to do that? Because Igor and Carmel change the same page. Carmel change here, Igor change here. I have only those changes. So it has to happen, or maybe they did partially overlapping change or something like that. I don't know. I have to do it in the appropriate order, and I have to follow the whole sequence. Once I've done that, I verify that the state of my file is equivalent to the state that I have on the disk. And so the state in memory is equivalent to the state that I have on the journal. Okay. So file management. File management is how we actually work with the files. We do not append to the file. We always allocate space and reuse that. So for example, we have a 1 GB file. We want to add another byte. We would allocate another gigabyte all at once. Why do we do that? Because this is a very strong hint to the file system. Give me continuous disk space so I can work with it. To a very large extent, we try to reuse files. I gave you the example of how we do it with journals. We also do that with scratch pages as well. We'll talk about it in a bit. Okay. So let's talk for a little bit about scratch pages. Okay, what is a scratch page?
Copy.
Sorry?
Copy.
It's a copy. I copy the data from here, put it here until I can come back and write it to disk. Where is that page sitting? Where is it located? What do we do with that?
Memory.
Okay, so one option is to use memory, but that actually has a huge problem. You're a read transaction and you hold the memory stuck for a very long time. You would fill my entire memory. So in order to avoid that, Voron uses mmap files for scratches as well. So those are files that are mapped into memory. They are persistent. So if there is a memory pressure, the operating system can write those pages to disk and not worry about it. Which means that if I have a very big backup operation and lots of writes, in the meantime, what would be the impact of performance? Oh, I am going to have a lot of scratch files, but that would be it. Oh, get better disk is much, much easier than get better memory. It also means that we have to deal with another aspect. Let's assume that we are doing that on Azure. And Azure has really bad file I/O in many cases. And I had a backup transaction, and it lasts for 2 hours. And then the system crashed when I have a lot of writes in the middle. What happens then? Well, I have a lot of scratch files, but I keep the process, so they are done. They're not no longer relevant. But we also have another thing. We couldn't commit to the database, so we have a lot of journals to go to. And that means that when we start going through all the journals and update all of those pages, which effectively means that we have to do random I/O. At the end of recovery, the state of the mmap file is identical to what we have in the journal. It is not the state of the file on disk, because we have it flashed and committed that. And the reason we don't do that is that if we do that during the recovery process, well, I just modify, 5 gigabytes all over this very big file. Writing that to all of the application would be extremely expensive at a critical point, database load time. So we're doing that. We are not doing that. We are letting the usual mechanism that happen in the background to manage this. Okay, so we don't trust the disk. After I explained that, yeah, we have the journals and transactions have checksums, blah, blah, blah. Pages also have checksums. When we read a page for the first time from the disk, we verify this checksum. Why do we do that? Because it validates that the file wasn't, the page wasn't modified. If we have a bit flip, for example, this can be extremely nasty to deal with. Because we have a page sum, then we can detect that as, oh, there is an error, instead of having a memory corruption or something like that. But that leads to a different problem. How do we detect force read if we're using mmap? How do I know that I didn't already call this checksum validation? And the answer is that we have an internal bitmap that we set whenever we look at a page. So it is possible to validate the page multiple times, but we don't actually care that much about it because, okay, it's good. So whenever we load a page, we check if this is already been verified the checksum. If not, we run the checksum and then update this bitmap. Okay. I don't know if you noticed, but everything that I talk about for the past hour or so, just about pages and binary data. We haven't even touched on data structures. This is at a higher tier. Most of the data structures that Voron offers is some kind of a binary of B plus tree. We have fixed trees, we have compact trees, etc. There are standard binary trees, B+ trees that allow us to do order search or something. I'm assuming you're familiar with that. If not, we have to do another talk. Okay. Voron has this notion of tables. What is a table? It's just location of pages on the list that we can store some data and associated indexes with this data, which is just a bunch of trees that we use to record and iterate over the data. The idea here is that the table owns and manages everything around that. So here's the idea. How do we use a table? We have a few operations. We have a read, give me by the storage key, pretty much, or give me by a primary key, which uses an index to search for that value key and then get me the storage ID and then go to that. Or we can do seek forward, seek backward over the index data, which is effectively just a sorted values that we can do that efficiently. Indexes are typically local to the table that we use them for, but we also have a trick where we use a single index across multiple tables. This is how all documents in RavenDB are using the same key space. This is how I can create user/6 as a collection of orders. Okay? So, by the way, at this point, I would consider it to be a mistake. It would have been much easier to have separate spaces to all of those. But one of the things that is where this is super critical for us is on ETAGs. ETAGs is the global sort order of operations in the system. This is absolutely something that we care about to have across different collections. Okay, things that we haven't talked about. Voron has free space management. So when you modify a page or you allocate a page or free page, all of that is handled internally. We're not freeing the disk space back to the operating system. We have the scratch page that we talked about. We're talking about pages. The pages are actually composed of header, metadata, and the actual data. This is more or less about how you utilize that, etc. I'm skipping those details, they're not that important, and if you have questions, feel free to ask right now. In hindsight, I would do a bunch of things differently. We use a single big file for everything, which means that it complicates our life with regards to managing disk space. User has a reasonable expectation, just deleted the big collection. I want to see that show up on the list. Right now, pages and headers are in the same page. It would be more efficient if we had the headers in one location and the pages in another one. Remember that I said that OS pages are always 4 kilobytes? That's not actually true. You also have 2 megabyte page size and 2 gigabyte page size. And those allows you to reduce the number of lookups the CPU needs in order to find the relevant table. So slightly more efficient in this regard and very well suited to what we actually want to achieve. And I would like to thank them for suggesting this topic. Yes, and if you want help with something like that, give me a good topic to talk about.